All right. Thank you so much for joining, everyone. And to all of you who are new and have not attended any session before, hi, I'm Pooja Kulkarni. I'm the founder of Psych rstats Club. And Psych rstats Club works towards making statistics and R more accessible. And today we are very happy to be collaborating with Arjun for this workshop. And Arjun doesn't really need an introduction. You all must be already be following him on LinkedIn. So Arjun is not only a counseling psychologist, he does phenomenal work to make statistics and research more accessible and easier to understand, helping improve publication in the field. And so today, Arjun will be covering the statistics part of the session. And after him, I and our core team member Ritik Gupta, we will be covering the R part of the session. So without any further ado, Arjun, I invite you to take the floor.
Great. Thank you so much, Pooja. Thank you, Ritik, for having me here. I had been following you for quite a while, and I'll be honest, I jumped a little with excitement when I got your email about this collaboration. So, thank you for having me. I'd just like to get to know the people here so I can understand where you're coming from. Can you just drop in where you're studying right now, which university you're in, and which course? Just two things: the course you're in and the university you're in. You can drop it in the chat section whenever you're ready. Great. I'm seeing a lot of Delhi, Bangalore, AUD as well. Nice. That's my alma mater. Okay, so if I'm getting it right, most of you are from bachelor's right now, and I'll keep the conversations that we have to that level as well. If you have any doubts, any questions in the middle, please feel free to ask them. Don't hesitate. We'll take this very slowly, making sure that you understand everything that we're talking about. Don't worry about that at all. Hello, fellow Crustites. Congratulations on the very, very rigorous course that you're going through, wherever it is. All the best. All right, so let's get started on the topic that we have today, hypothesis testing and the p-value. Before that, before we get into hypothesis testing, let's first talk about what is a hypothesis. So a hypothesis is basically a statement or a possible solution for a problem that we have. But just because we have a hypothesis doesn't always mean that we are right. Take this as an example. Can you make a hypothesis for this? This is who's that Pokemon? I hope you understand who Pokemon were. I hope I'm not too old for that. So can you guess who this Pokemon is? Cannot recall. Okay, great way to make me feel old. No problems. Uh, Bantwal is saying Ductrio. Isha is sure this is not Pikachu. Frederico is saying Diglett. Yes, it's clearly been a while. Okay. Now, this is what we are doing is basically we're forming a hypothesis where we have a problem in front of us and we are looking for possible solutions for this. And then we find out that this is actually Uncle Ben's graveyard. Sorry, Peter Parker. So we can take two lessons from this. Number one, a hypothesis is tentative. We can't be sure about whether our answer is correct or not. We can only tested against the evidence we have in front of us. We can't say anything with certainty when it comes to a hypothesis. Secondly, hypothesis is determined by the research question we have at hand. You only guessed the different kinds of Pokemon because I told you that we are looking for a Pokemon here. We are looking for who's that Pokemon was the research question. in this situation. And so we get two conclusions here, that number one, hypotheses are never certain, they're always tentative. uh, yes, Arya, I know I said Pokemon, and sorry about that. थोड़ा सा mislead कर दिया मैंने. And secondly, that we only get our hypotheses are ultimately determined by the research question we have at hand. With this in mind, you might ask, why do we need hypothesis testing in the first place? And we come to that with this study done by Doob and Gross in 1985. Um, this was a study called The Status of Frustrators as an Inhibitor of Horn Honking Responses, done by Anthony N. Doob and Alan E. Gross from the University of Toronto and Wisconsin. Now, what they did was they wanted to understand whether the status of a car determines how much honking a person does when they're situated behind that car. So here we have a low social status car. It's very old, it's very rusty, and when it cannot start its engine the moment the light turns green, will the person in this car honk or not? This is situation one. Second, they put a high-end car here. They put a Porsche. It was very new, very valuable. And when that car failed to turn on at a green light, will the person honk their horns or not right behind their cars? This is what they were trying to study. So this is the question here: is does the status of the frustrator act as an inhibitor of horn honking responses? That's what they were going for. What they found was, for the old car, 84% of the people right behind this car honk the moment the light turns green and it does not start. Whereas for this one, for the new high end car, that number is only 50%. They did another level of the study. Do the people honk twice? Now these people were located in the United States. They don't really have a honking culture there. If they were in India, I can assure you it would have always been 100%, no matter who it would have been. But when they wanted to understand whether people honk twice as well, the numbers were similar. For the old car it was 47%, and for the new car it was 19%. Now, what do we get from the data that we have here? What can we think of? Why did we observe this disparity? This can be due to a lot of factors. You can share your thoughts in the chat section as well. It can be due to simply the people who were parked behind this car being more prone to frustration. Maybe they were just unhappy in general. Maybe the people here were more mellowed out in general. Maybe it was just a sampling error. Maybe it was a difference of the time of day. People are in a hurry during the mornings and the evenings, so they wanted to get home or get to the office as quickly as possible. There were an n number of factors that could have played a role here. As Varshita is mentioning, personal biases could have played a role. Every person is different and they have different horn honking responses. We can't know for sure. But how do we know beyond a reasonable limit that this did not happen due to chance alone? That this was not something that was random. This was something that actually had some tangible reasons behind it. We do that by involving numbers. We include data. We test hypothesis because data, by its very nature, is ambiguous. The numbers that I showed you, 50% at 84%, they mean nothing by themselves. We need to infer meaning from it. And that is what we do when we are testing our hypothesis. A very common question in this scenario is what kind of a hypothesis test we should use. Now, that is a whole discussion in itself, but I'll give you an overview of which tests you can use. It largely depends on two things, the kind of test that we will use. It depends on the kind of question we have and the kind of data we have collected. What does this mean? So let's first talk about the kind of question that we have on our hands. If we want to compare the differences between two groups, as we were trying to do in the example that I just shared, we were trying to understand were there differences between uh, the two groups, the old car and the new car. Was there actually some non-random reason for that? In that case, we use these tests: the T test, ANOVA, Z test, ANCOVA. You don't have to understand them right away. You just need to understand what these tests do in general. All of these tests help you differentiate between two groups. Whereas if you want to see the relationships between two groups, the strength of the relationship, or whether one can predict the value of another, in that case you use different kinds of correlation or regression. Is it clear till now? Just send a thumbs up if it is. You can choose that in the react section. Yes, Mohit. Okay, great. I think I'm seeing most thumbs up. If you have any questions, please feel free to ask them. You can raise your hand and put your thoughts here as well. Okay, no worries,
I
Mohit.
think Arjun, you can just continue. If someone has any question, I'll ask you. Yeah, in
Yeah, yeah,
between. Yeah.
sure. I just keep like to keep checking in every once in a while to make sure I'm on
Sure.
the same page. Yeah. Okay. Next is the type of data that we have, and the data that we have is practically of two types. Sorry, it's getting very hot. Just give me a moment. There are two types of data that we collect in psychology. One is the categorical data, and the other is continuous data. Categorical data is data that exists in the form of categories. Think of eye color, hair color, or the type of car that we're driving. Those are all forms of categorical data. There are very clear categories, discrete categories that we have. You can have blue eyes, brown eyes, black eyes, all these kind of eyes. You can't really have a mixture of the two of them unless it's a very rare case. Whereas for continuous data, it's something that is more linear. It is on a continuum, so you can have a height of 175 centimeter, it can be 175.11, it can be 175.1111. It is all an infinite continuum that we have this data on. In this case, we use stuff like Pearson's correlations, repeated measures ANOVA, etc., etc. And for categorical data, we use the chi-square. Now, I will share a complete decision tree for your hypothesis test as a supplementary material added on at the end of this. The thing you have to keep in mind right now is uh, the kind of test we use depends on the kind of question that we're trying to ask and the kind of data that we have collected. Two basic things. Now we come to one of the most misunderstood and one of the most ubiquitous metrics in the world of research, and that is the p-value. The p-value is something that you will find in almost every kind of research across the world, whether it's in biology, chemistry, sociology, psychology, of course, us. Everywhere, almost every discipline uses the p-value in some way or the other, and yet it is one of the most misinterpreted metrics out there. So we are going to learn what is the exact meaning of the p-value and why it is so important to us. Now, before getting to the p-value, we need to understand two things first. That is the normal probability curve and the null hypothesis. I'll give you very short, brief refreshers or very brief introductions into what these are. So if you have not been introduced to these concepts before, please don't worry. Um, I'll make sure that you understand all of them as well as you need to for now. Okay. Um, but before talking about the p-value and before talking about all kinds of statistics in the first place, one thing that you need to accept and one thing that you need to understand is that in statistics, in we believe that randomness exists. Things happen without a reason as well. It is very common to believe that everything always happens for a reason. There is a reason behind everything. But in statistics, we have this very basic belief that randomness exists. Shit happens, and there is nothing, there is no meaning that we can derive from it. All right. Now that we have that out of the way, the p-value helps us differentiate randomness from actual meaningful things that we can actually collect from the data that we have collected. Right now, this is what the normal probability curve looks like. It is basically a distribution of different probabilities of an event happening. So, take the example of the Wechsler's intelligence scale for children. Uh, the intelligence scale has a mean of 100 and a standard deviation of 15. And that means that if I conducted this scale, if I use that scale on any one of you, I think there are around 67 people here. Yeah. If I conducted the scale on any one of you at random, there is a 68% chance that you will lie between 85, which is one standard deviation below the mean, and 115, which is one standard deviation above the mean. On the same grounds, there is a 95.44% chance that your IQ would lie between 70, two standard deviations below the mean, and 130, that is two standard deviations above the mean. We can understand probability from this graph itself. Secondly, the null hypothesis is the hypothesis of no assumed difference or relationships between our variables. It is a hypothesis that we create wherein we are saying that there is no difference between what we are measuring, there is no relationship between what we are measuring, and uh, there exists basically nothing between the two. So if I claim that the students who attend my workshops have a higher IQ than the general population, can you tell me what my null hypothesis would be? You can type it out in the chat section or unmute yourself and speak up. Yes, I think there's a raised hand. Yes, Shubham.
So there would be no relation between the IQ levels and the people who join the workshops.
Yes, exactly. So I'm seeing there is no difference in IQ of the two groups. There is no difference in IQ between those who attend and don't attend my workshop. Aditi is saying no relationship exists. We are trying to see whether there is some difference or not. So saying that there is no difference would be a better word here. Aditi. Shivali, same educational background. Again, that depends on the kind of sample I'm collecting. What I'm just looking for right now is what null hypothesis you would create. Okay, there is no difference, no difference, no correlation. Varshita, again, I am looking for differences between two groups. In that case, it's better to use there is no difference between the IQ levels of two groups than to say that there is a correlation between them. And just send a thumbs up if that is clear to you, Varshita. ठीक है बारबी कौन देख रहा है ओके नो नॉट द पॉइंट हाँ no significant difference, great job everyone. Okay, so this is the null hypothesis that we have created here. Now let's go back to the p-value and imagine that I actually tested whether students who attend my workshops have a higher IQ than those who don't. And this is the data that I got. The IQ of the attendees I have is 102, and the IQ of the general population, mean IQ of the general population is 100. That is, we take that as the assumed population, right? What would this difference mean? And for this, I got a p-value of 0.02. What we need to understand is what does this 0.02 mean? Now, when I ask students to define what or to interpret what this 0.02 means, they often use the words significant, non-significant, but we don't need to use those words when trying to describe or interpret the p-value itself. First, imagine that I run the same study with a new random sample 100 times. Okay? 100 times, I take a sample of people who have attended my workshops and the general population, and I compare their mean. I do this 100 times because I have a lot of time on my hands. In these 100 trials, it's quite possible that I'll get all of these following outcomes. Sometimes the IQ of the general population will be more than that of my attendees. Sometimes the IQ of the general population will be less than that of my attendees. Sometimes they both will be equal. Why does this happen? It can happen due to multiple of reasons, something as simple as sampling error. And whenever we are taking different samples from different groups, there will be some variation. Not everyone is the same, right? So it can happen due to a lot of reasons, but all these three are possible in the 100 trials that have gotten. What the p-value of 0.02 means is that in a world where the null hypothesis is true, In a universe where there is no difference between people who, in the IQ of people who attend my workshops and those who don't attend my workshops, even in that world, I would see the difference that I did 2 times out of 100. So if I did that study 100 times, I tested the IQ of people who have attended my workshops and those who have not. Even in that world, um, even in a world where there is no difference in the IQs, I would get a difference in scores more than or equal to 2% of the times. Because this is what I had gotten here. See, the difference between these is 2. And what the p-value of 0.02 means is that if I did the same study 100 times, I would observe this exact difference or something more than that 2% of the time, even in a world where there is no actual difference between the two. In other words, in other words, even in a world where there is absolutely no difference in the IQs of people who attend my workshops and those who don't, I would make this observation 2% of the time. Is this part clear to you till now? I'll happily repeat it if need be. Just send a thumbs up if this is clear. We'll do some solved examples as well, so don't worry about that. So yeah, I'm guessing this is all hand thumbs up so far. Yes, Fatma. Um, yes, of course, I can repeat. So let's go over this whole situation again. What I did was I tested the IQ of people who have attended my workshops and those in the general population. I got the IQ of my attendees at 102 and the IQs of my general population at 100. Now, I might say, obviously, this means that the IQ of my attendees is more, so they are smarter. I make people smarter with my workshops. But as I had just said, random shit happens. And we need to make sure that this is not due to randomness. For this, I got a p-value of 0.02. Now, this 0.02 means that if I were to do the study again 100 times, I did the same study, I took the IQ of people who had attended my workshops and those who had not attended my workshops 100 times. Even in that world, I would observe a difference like this 2% of the time. That is what this p-value of 0.02 means. So even in a world where there is no actual difference between the IQ of people who have attended my workshops and those who have not attended my workshops, even in that world, I would even in that world, I would see this 2% of the time. Tanisha, on what basis do we say it is 2%? That is how is p-value calculated. So that depends on the kind of test we are doing. If we ever get into the theory of the different kinds of tests that we do, whether it's the t-test or ANOVA or ANCOVA, all of them have different ways to calculate the p-value. That is a whole another workshop in itself. It's better to right now understand what the p-value means in the first place. Here, I am just saying, let's assume it as we got the p-value as 2%, 0.02. Is that clear? Varsha and Fatima, did that help? ठीक है. Now, this probability of 2% is quite low. But is it low enough to reject our null hypothesis? That is something that is decided by our level of significance. We can set it at 5% or 1% or 0.1%. We can set it wherever we want to. कि अगर हमारी p value, if our p value is lower than this much, then 5%, we will reject our null hypothesis. or if it is lower than 1%, we will reject our null hypothesis. It is ultimately a decision the researcher makes. It is not something that is bestowed upon us by numbers themselves. It's just a general convention that we are following. So let's do a solved example first. Imagine that I'm testing whether eating spinach improves reading scores compared to children who don't eat spinach. And I get a final p-value of zero point 0.2. How do I interpret this? Now, this means that in a world where there is no difference in reading scores of children that eat spinach and those that don't, I would observe the data I did 20% of the time. I'm not going to tell you what the data that we collected was because that will only complicate things for you. I'm just telling you that a p-value of zero point 0.2 means that we would observe that data in a world where the null hypothesis is true 20% of the time. All right, let's make you do one of these now. So while testing if men have higher emotional vocabulary than women, you observe a p-value of zero point 0.5. Can you interpret this now? You need to do two things. First is, in fact, give me what your thoughts are, give me your answers, and we'll discuss them very shortly. Mahalakshmi is saying that it's not significant as it has to be less than 0.05. Again, I'd encourage you to interpret this without using the words significant or non-significant. Sneha is saying same observation 5% of the time in a world where the null hypothesis is true. Sneha, I think what we have is P of 0.5, which would make it 50%. I think that's a small mistake that was made. Yeah, 50%, correct. Sonia is saying that at least 50% of the time you allow yourself to see that difference. Okay. If we were to accept the null hypothesis, we'd have to observe the data 50% of the time. Yes, I think Tanisha's response is the most appropriate one I've gotten so far. And Arya's. I'm just thumbs upping them so you can see them as well. Yes, Fatma, there's a 50% chance we would observe the data that we did in this. Yes, Bhavika is correct as well. The thing about this is we don't really know whether the null hypothesis is true or not, and the p-value does not tell us those things. The p-value is a measure of probability only. It is the measure of probability of something happening in a world where, in a universe where the null hypothesis is true. We are not saying that the null hypothesis is true. We're saying if the null hypothesis was true, we would observe this data 50% of the time. We often make that mistake of thinking of the p-value as an arbiter of truth or reality. It is simply a measure of probability, nothing more and nothing less. ठीक है. As a supplementary material, I'll share some more worksheets on this so that you can sit at home and interpret different kinds of p-values by yourself, and a paper on the common misinterpretations of the p-value as well, so you understand what mistakes to not make. All right. Now, throughout this, you might be asking that I asked you to do two things to understand the p-value. That was understand the null hypothesis and understand the normal curve. But we have not really talked about the normal curve here. So let's turn the things we have talked about here into a graph. First, let's talk about why this normal distribution is so common in psychology and why it is so important. That is because we work on the assumption that traits in psychology are normally distributed. Think of it this way, that most people, no matter what trait you can think of, extroversion, introversion, intelligence, all of these traits are normally distributed, which means that most people are average. As you'll see in this picture, I'll just go there. Most people are average, they're on the center. Some people are on one extreme and some people are on the other extreme. Okay? This is a very basic assumption that we work on in statistics. So imagine we are testing whether brain training increases IQ. Now, in this situation, can you tell me what the null hypothesis would be? I'll ask you to form a null hypothesis once again. Can you tell me what my null hypothesis would be if I am saying that brain training increases IQ? Or that I'll rephrase it, that there people who receive brain training have a higher IQ than those who don't. ऐसे सोच लो. Yes, Sonia, correct. Brain training has no impact on IQ. Very good. Brain training doesn't increase IQ. Correct. Perfect, perfect. Now, in this situation, we don't know whether the null hypothesis is true or the alternate one. The alternate one in this case would be that brain training does increase IQ. But we work on the assumption that the null hypothesis is true. And this is how our null hypothesis is distributed. Again, this is something we are working on an assumption. Okay? Here, what we do is when we are testing our hypothesis, we set a level. Uh, this level of significance, this red line. I hope this is visible to everyone. We set this red line and say that if the data we collect is on this side, on this end, we will reject our null hypothesis. Is this visible? I'm not sure if it is. I think it's a bit on the lower end.
It is visible, Arjun.
Visible? Okay, great. So we say that this is our Lakshman Rekha, this is our level of significance. If our data is towards this side, we will reject our null hypothesis because it will be too rare to observe. All right. You will notice that there is this small portion, red area, where the data is actually from our null hypothesis, but if we collect the data only from this area, we would still be rejecting the null hypothesis because it is beyond our red line. So the data will be coming from this area, but we would still reject our null hypothesis because it is to the right of our Lakshman Rekha, our red line, right? This is known as a false positive or a type 1 error. We are rejecting the null hypothesis even though the data is coming from our null hypothesis. This is known as a false positive or a type 1 error. The same way, our alternate hypothesis is usually normally distributed as well. It again looks like a normal curve, and we don't know how it is located with respect to the null because again, this is an abstract world that we are living in. So it could be placed somewhere like this. This is the IQ of people who don't receive brain training. This is the IQ of people who do receive brain training. It could also be something like this. It could be like this. We genuinely don't know. Again, let's work on the assumption that this is how these two are arranged. The red line, as I said, is our level of significance. Okay? In this case, you will observe that there is this small blue region where the data is actually from our alternate hypothesis, but because it is not beyond our red line, we will not reject our null hypothesis because it is before it. And we have set our line here that only if the data is beyond this line, will we reject our null hypothesis? This blue region.
Arjun, sorry for interrupting, but is
Yeah,
it possible to like scroll it a bit upwards? The blue part is not
yeah.
entirely
That's
visible.
what I'm thinking as well. Just give me a moment. I'll shift it all up.
Yeah, much better. We can see it.
Right? I'll just do this
Yeah,
on the
thank
rest
you.
as well. I think that should help. Hanji. Hanji. Now, in this case, what we have here is that there is this blue region where the data that we have is actually coming from our alternate hypothesis. But because it is not beyond our red line, we will not reject the null hypothesis. And this is known as a type 2 error or a false negative, wherein we don't reject the null hypothesis even when it is false. Okay? The probability of this type 2 error is determined first by where you set your line. I'll show you the relationship between them in the next slide, and the difference between these two curves, among other things. If this curve was located somewhere over here, assume it looked something like this here. In this case, you'd see tiny region, the blue region that I had drawn from the purple curve beyond before this red line is just narrowed. It's just this much that is left, right? So it depends on the distance between these two curves and where we have set our red line. Take this as an example that I don't want to have the error of the probability of a type 1 error that large. This is where I had set my old one. And for me, that type 1 error was too large. So I shifted the red line over here, that I am reducing the chances of making a type 1 error. But in doing so, I have now increased my chances of committing a type 2 error. So clearly the two are related. If you increase one, you will decrease the other. And if you decrease one, you'll increase the other as well. The main thing that you need to understand here is that we cannot ever completely escape error in our hypothesis tests or in our research. There will be some degree of error that there will be in our research. What we have to do is minimize it as much as possible. What is the general conventions on how much error is acceptable? In general, alpha is set at 0.05 and beta, the chances of making a type 2 error are set at 20%, 0.2. Okay, these are again general conventions. There is nothing hard and fast here. This is just something all of us have decided is the norm together. ठीक है? But there is another element here that this graph can teach us. Look at this yellow portion here. This yellow portion is the probability that the data that we have is coming from the alternate hypothesis, right? And because it is beyond our red line, we would reject the null hypothesis if our data came from here, this yellow region. This is the probability that we would reject the null hypothesis when it is actually false, this whole yellow region. And that is known as the power of a study. The power of a study is the probability that we would reject the null hypothesis when it is false, that we would observe an effect when there actually is one. How to interpret this is that a power of 80% means that 8 times out of 10, if we do the same study again and again 10 times, 8 times, the study would find a significant difference when there is a true effect, and 2 times we would get a false negative. That is, we would not find a significant difference even if it is actually there. That is, we would be committing an error. So let's just do a very quick pop quiz that if I tell you that the generally accepted beta is zero point 0.2, that this region is zero point 0.2, I'll shift it up again. Just give me a moment. Hmm. If I tell you that this region is point 0.2, the area of this is point 0.2, can you tell me what this area would be? The generally accepted beta is point 0.2. So can you tell me what the general expectation of our power is? Hint, this whole graph has a total area of 1. Point 0.8, point 0.8, point 0.8. Correct. And that is why the general convention of the power that we expect in our studies is set at 80% power. We expect our studies to have 80% power. The problem is most of the studies that we do in psychology at a UG level, at a PG level, they barely cross the 10% or the 12% mark. How do we calculate the power? That Ritik will discuss in the next section. But having a powered study is very important because that makes sure that we don't, that we actually have the capability of finding an effect when there actually is one, right? So let's just go over what we have learned today. We first talked about why we test hypothesis. We then talked about what determines our tests. We talked about how to interpret the p-value and the level of significance. Then we talked about type 1 and type 2 errors. And at the end, we talked about power, why it is important, how do we calculate it, that will be discussed. But we just got a way to visualize what power is like. And with that, I think it's a good place to conclude my section where the statistical part, and Ritik will take over from me and talk about how we can do all these things in the R studio with a general introduction to R as well.
Thank you so much, Arjun, for that wonderful presentation. We really love your slides and all the examples. It was really amazing. By the way, if anybody has any questions, I think we can do some questions before we move to the R part. And for the R part, I will just quickly introduce the R environment, and then Ritik will be covering the statistical tests in R. But before that, does anyone have any questions? Yeah, you can unmute and speak. Someone has raised their hand. Federico.
Um, are you able to hear me?
Yeah.
Yeah, we can hear you.
All right, thanks. Nice presentation, mate. I only have one doubt, and is that if there is any use in conducting hypothesis testing for finite populations. Let's say you have a data set that covers all the information that you can have. For example, something from Spotify, and you are collecting all the data on a particular artist. So, is there any use in conducting a hypothesis test for those scenarios in which you are not working with a sample?
Interesting question. I'm not really sure. I think this is more in the domain of market statistics. I'm not really sure if I can answer that appropriately right now, Federico. How about I get back to you on that one in a few days?
Okay, thanks. No worries. It's a big doubt that I've been having for a while now, so don't worry about that.
Yeah,
Thanks.
fair enough.
I think there's one question in chat. Can you please explain types of errors?
Yes, I can. So the type 1 error, I'll just show you a very popular image I love to refer to. Um, the type 1 error is basically when you reject the null hypothesis when it is actually true. Okay? Whereas the type 2 error is when you fail to reject the null hypothesis even when it is false. And that is something that this image might be able to help you. Yeah, so this is a type 1 error where you're giving a person a false positive. You're telling a man that they're pregnant. It's a case of a false positive. Whereas type 2 error is you have a lady who has just had her water broke and is um, about to give birth, but you're telling her that no, no, you're not pregnant. You don't have a baby inside you. In that case, what we are doing is that we are giving a false negative. That even when the baby is right there, we are still saying that there is no baby. Radhika, does that help a bit to visualize what these are? Oh, sorry, that was Sneha. Sorry. Radhika, you're asking whether the p-value is enough to reject or accept the hypothesis. So no, it is not. It depends on where we are setting our level of significance. Sometimes we can set it at 0.05. Sometimes we can set it at 0.01. It depends on where we're setting our alpha. That defines whether we can reject or fail to reject our hypothesis. And we don't accept our hypothesis ever. There is no situation where we accept our hypothesis. Yes, Manvi, I can summarize the power of a test. So, see this as an example. Uh, Hanji. Now, when you look at this graph, what you have here is that this is the level of significance that we had set. And we had said that if any data lies towards this side of it, we will reject our null hypothesis. All right. Now, what happens is that given how the null hypothesis and the alternate hypothesis are shaped, we get this area wherein the null hypothesis is false. The data that we are getting is from an alternate hypothesis, and we are still um, rejecting our null hypothesis. That is, we are making the right decision. We are rejecting our null hypothesis even when it is false, and that is the power of a test. That is the ability of a test or the ability of a particular data set to find something when it is actually there. That is the role that power plays. And unfortunately, a lot of the studies that we do are very underpowered. I think we might discuss a few cases of how to calculate power. Uh, Pooja, do we have that? Are we discussing that?
Actually, today we don't have time to discuss power a lot. We are going to be looking at how to conduct different statistical tests, and
Mm-hmm.
we will be looking at some of the basic functions in R. I'm not sure we will have enough time for power.
No worries.
So we were, yeah.
I think I can contextualize from the test themselves. If something comes up, we can cover that. Varshita, how do we find the p-values? That's again something we will discuss when we are conducting all our analysis. That is when we find out our p-values. Most of the time, the softwares do it for you as R or SPSS, whichever one it is. I think a lot of these doubts will get cleared out once we have the visualization of R.
Yeah, don't worry, everyone. We will have the R part where a lot of these abstract things will get more concrete. So, yeah.
Shivani, I think that will answer your question as well.
Okay, thank you so much, Arjun, for answering these questions. And I think we are good to go to the R part of the session. If in case anyone still has any doubts, feel free to uh, email us and we can forward those to Arjun. whatever you have. You all already have our email. We have the one with which we send the meeting link, so you can email us later. So if there's so we will move on to the R part of the session now. First, I'll just introduce the R environment, and after I introduce the basic functions in R, Ritik will be covering how to conduct the basic statistical tests in R. So yeah, and before I begin with my part, I'll just quickly give a little bit of more background on myself. So hi, I'm Pooja Kulkarni. I did my master's from University of Mumbai in applied psychology, and I started this Psych rstats club when I was pursuing masters, and the aim has always been to take efforts towards reducing barriers in statistics and our education. And I'm lucky to have found a great core team who are as passionate about this cause, and also amazing collaborators to help us with this mission of making statistics and R more accessible. So yeah, I will cover the basics of our environment, and later our core team member Ritik Gupta, he will cover the statistical tests in R. So I'll just quickly share my screen and start with the R environment introduction. Can everyone see the R Studio screen now? Ritik, can you confirm if it's visible?
It's not yet.
I have
Yeah,
shared
I
my
can.
screen.
Okay, yeah,
I can.
now it's visible. Yeah,
Yeah.
go ahead.
Okay, great. I'll turn off my camera just because I'm not sure about how strong the internet is. So yeah, okay. So what you see here in front of you right now, this is the R Studio screen. And do not get overwhelmed right now. You might be wondering what these different things do. We will go step by step. So first, to begin with, let's discuss what exactly is R and what is R Studio. So R is the programming language which was specially developed for statistical computing, which means that it has many functions and many packages which make it much easier to analyze your data. And it is very popularly used in psychology and social sciences to analyze large data sets. So yeah, R is a programming language, and R Studio is the IDE, which is Integrated Development Environment, which means it's a software which makes it easier to code in R. So what you see in front of you, this is the R Studio screen, and in this R Studio, we will be coding using R. Now, I will show you all how to install R and R Studio in case you don't have it installed already. So in order to code in R Studio, you need to first download R and R Studio. So on the first link, if you go to this first link, RAN website, and don't worry, we will be passing on this file to you later. So if you are doing it in your own time, you will still have these links. So I'll just show you all what this would look like when you try to download R. So the first is the link to download R. And if I paste this here in the browser and open it, you will see this page. So this is the CRAN website which hosts the different versions of R. And here you will see the options to download the latest version for R, and you can click here whatever operating system you have. You can choose from this option. If you have Windows, click on this download R for Windows. If you have Mac, you can choose this option. So for me, I have Windows, so I'll click here. And you have to go to this first option because as you see, it's written here, if you are installing it for the first time, you have to select this one. So once you click this, here again click on download for Windows. And once you click this, it will start getting downloaded. But I will cancel this right now because I already have it downloaded. Okay, so this was how you download R. Now coming to R Studio, the second link that we have here, this is the R Studio link. If you open this in your browser, it will look like this. Give me a moment. So yeah, this is the R Studio website. Here you can select download R Studio. Because you have already installed R, you can skip this step and directly click on this install R Studio button, and it will start getting downloaded. I'm canceling it because I already have it. So yeah, what you downloaded now, it's the exe file. And in order to have it installed on your laptop, just click on the exe file and the setup wizard opens up. It's very similar to how you download any other software on your laptop. You have to follow the prompts, and mostly you just have to click on next, finish, and it will get installed on your laptop. And once it is installed, you have to open this R Studio. This is the R Studio icon. And if you don't find it on your desktop, it will be in program files, or just search for R Studio. And once you open R Studio, your screen would look something like this when it's new, and it would be white for you because that's the default color. I have changed the color here, but don't worry about colors right now. So it would look something like this, and there might be some words here for you. Now, in order to start using and to start coding in our studio, you need to create a R file. So there are many different kinds of files which you can create. I will start with the R script file, which is a basic R file where you can start coding. So in order to create R script, you can see this green paper icon, right? So once you click here, you can click on R script, and this R script file will be generated, and you can start coding here. So on your screen now, you should have these 4 different sections, and I'll quickly talk about what these different sections of the screen do. Before that, I'll also show you all how to run some codes in the R script. So if I want to run a code here, I'll just type it. So for example, I'm writing 2 plus 2. In order to run this, you can click on this run button here, or you can click on Control and Enter on your Windows, and or you can click on Command plus Written, if I'm not wrong, on Mac. So that should help you run the code. And once you run this, the output will appear below over here. This is the console pane. So whatever code you run in the first pane, which is called the source pane, the output for it will appear mostly here in the console. And console pane also allows you to quickly run some code. But the difference between this pane and the console is that whatever you type in console, you might be able to run it, but you won't be able to save it as a separate file. So if you want to code and save it as a file, make sure you type it here in the R script file, and later on you can go in file and save it. So yeah, so as you saw this where we code, this is the source pane. Here where you get output and where you can test out certain codes, this is the console. And on the top right, this is the environment pane. So environment pane is where you will see all your data sets that you import, and whatever objects or variables you create in R, those will appear here in your environment. And below it, this is the output pane where you will see the output for your graphs and plots. And basically, this pane has a lot of different functions. As you see, there are these different tabs. So, but mostly you will be seeing your charts and plots, whatever you create, that will appear here in the output pane. And later on, this packages tab, it will also allow you to install packages. Now, in this workshop, we won't be discussing different packages a lot, but just know that packages are just a set of code that is not built into base R, but it is something that you need to install. And packages have many useful functions which are very useful later on and which are not available in base R. And that is when you have to install these packages. So this tab helps with installing packages. But for now, we will work with just base R. You don't have to install packages for now. So yeah, this is the output pane. And don't worry if all of this sounds very vague or abstract right now. As you start coding, slowly you will start understanding what these different things do. And slowly it becomes second nature to you. So yeah, now coming to what we have here. For this session, we have created a R Markdown file. Now I showed you how to create a R script, but we have created a R Markdown file for this workshop because R Markdown is just another type of file which allows you to combine text along with code. So when you are giving workshops or teaching something, it comes very handy to combine text, that is the explanation for the code here. So we have created this R Markdown so that we can include the explanations for the code here. And we will be sending this file over to you. So when you are practicing on your own, you will be able to understand what these pieces of code do. And you can also create R Markdown by clicking here and choosing R Markdown. But don't worry, for now, you can just, whatever code we have here, you can type it in your R script file. And the code part is here between these quotes. So whatever you see between these quotes or the R bracket, here this is the actual code. And outside of this is just normal text. So yeah. All right, now coming to basic functions in R. In R, you will mostly be analyzing data. And one of the key reasons R is helpful for beginners is also because it has these beginner-friendly built-in data sets, which come in handy when you are starting to learn R for the first time. So these data sets have been built into R, which means that you don't really have to download any other Excel or CSV data file to start analyzing. These data sets are already available in R. And in order to access these data sets, you need to type this line of code, data and the circular bracket. So, and you need to remember that each line of code in R has its specific purpose. And slowly, as you start coding, you will just understand what these different things do. Right now, you might be thinking that you need to remember this, but slowly, as you start using it in your daily life, it becomes second nature to you. So for now, just know that this data and circular brackets, this allows you to view the built-in data sets in R. And in order to run this, I will click on this green button here. But in your R script file, you can just click on this run button, or you can just press Control and Enter on your laptop. So when I run this, I will get this list of data sets that have been built into R. Now, as you see, there are many built-in data sets. These are the names of the data set, and this is just a short description of what they are. And from these built-in data set today, we will be working with Iris. So Iris is a very commonly used data sets. If you see any R tutorial, it's very commonly used because it's very beginner friendly and easy to use. So just note down this name, copy. And if you want to know more about the Iris dataset, you can just type its name and put a question mark in front of it. Whenever you put a question mark in front of something in R, it tells R that you want to know more about it. So it will give you more about that particular thing. So because you have typed the name of the dataset here, it will give you more information about it. So as you see here, I get more information here in the help section of the output. So it says this is the famous Fisher-Anderson's iris dataset that gives measurement in centimeters of variable sepal length, width, and petal length and width for 50 flowers of 3 species of iris. So you get a quick description of what it is. And now coming to, so now we saw how to access the built-in data set. Now coming to functions, some basic functions in R. So a function in R is basically a line of code which has a particular purpose and it has to be written in a certain way. So we will look at some basic functions in R. So for example, this dim function allows you to view the total number of rows and columns in a data set. And in order to do that, you first need to write this dim circular bracket, and within it, you have to mention the data set name. And when you run this, I get two values here. Now, the first value will always be the total number of rows, and the second is always the total number of columns. So this just, if it's a large data set, instead of scrolling through the entire thing, you will just quickly get an idea of how big it is. So you can use this dim function then. And if you actually want to view the data set, you just have to type its name. So if I actually want to see the data set, I'll just type its name Iris over here and I'll run this line. So when I run this, I will get the actual data set here. As you see, it shows 150 rows total. And here you see the columns. All right, so this is how you view the data set. Another way to actually view the data set is by creating a data frame. Now, data frame in R, it saves a data set as a table object. So when I create a data frame, it is saving it in table format. Now you'll understand when I create it. In order to use data frame function, just write data frame, and within circular bracket, you have to write the data set name. So what this does, it will save it in a table format, which you can view. So if you click here, you will be able to see the table here. So this also is very useful when you're working with your own data set. You will be creating data frames out of it and storing it in another variable. So what you see here, this arrow, this is called an assignment operator in R. So whatever comes before the arrow, that is like a placeholder or a variable which you're creating, and within it, you will be storing this data set. So because this data frame created a table and we assigned it to A, now that table is referred to as A. And whenever you want to access the same data set, you can just simply refer to it as A now. So we saw how to create the data frame. Now coming to another basic function, which is the head function. If you want to quickly get an idea of what kind of values there are in the entire data set, scrolling through all the rows of data is very time consuming. So if you just quickly want to get an idea of the kind of values, you use this head function. It just prints the first 6 rows of the entire data set. So it will print all the columns and it will print the first 6 rows. So as you see here, you get the first 6 rows of these variables, and you can see the kind of values that are there. Now we saw some basic functions and built-in data sets. Coming to how to import your own data set. Now, as a researcher, most of the time you would use R to analyze your own data. So in order to analyze your own data, you first need to import it into R. And the way to import your data set, there are actually several different ways. One way is to use this import dataset option in the environment tab. So click on this import dataset option, and here you will see several different file types that you can import from. For example, if you want to import from SPSS data, you can select one of this. Because I want to import Excel for now, I'll click this import Excel, and I can click on browse, and I can select whatever file I want to import. So for now, I'm importing this file just to see how it works. And R will also give you a preview of the data over here. And then you can just click on the import button here and it will be imported. As you see, it has been imported here in the environment tab. Now, this was one way to import your data set by clicking on buttons. But another way to import your data set is by actually typing lines of code. And one benefit that actually typing it out in your code does is that when you are passing on the file to someone else, the code captures the fact that you are importing this particular file in the code. So another way to import your data set is by typing out lines of code. Now, in order to import your data set by typing code is by using this read Excel function. Now, read Excel function in R, it allows you to import an Excel file. But in order to use this read Excel function, you need to install the read Excel package. This is because read Excel has not been built into base R. You need to actually install the read Excel package. And only then you will be able to use this read Excel function. And the way to install the read Excel package is by just writing install.packages, and within the circular bracket, just type read Excel. Also ignore this hashtag. This is written here just for knitting purposes. When you type install.packages, just type install.packages and in circular bracket read Excel. And after that, type library read Excel. So these two lines of code, it will get the read Excel package ready to use in your R. And once it is installed, then you can start using this read Excel function. And just type read Excel. And within it, I have used file.choose function. So this function has another purpose. What it does is, it opens up a dialog box for you from which you can select your Excel file. And sheet equals to 1 tells R that whatever file you are selecting here, from it you want to choose only the first sheet. So together this code, what it does is it helps you import a Excel file by opening up a dialog box, and within that it will choose the first sheet of whatever file you use. So if I run this, now let's see what it does. As you see, it automatically opened up this dialog box for me. And from this, I can again choose the Excel file I want to import. So now you can see that it has been stored as DF this time. This is because we assigned it to DF. And from now on, whenever you want to use that data set, you can refer to it as DF. And if you want to view what DF looks like, you can again use the same head function, and it will show you the first 6 rows of DF. So as you see, it is the same data set, 100 observations of 4 variables. So yeah. So we saw 2 ways to import read Excel. One, we saw how to do it with the import dataset option, and second, how to do it by using read Excel function from the read Excel package. Now coming to another type of file, which is very commonly used. Another type of file is CSV. This is also very commonly used file type. And in order to import a CSV file, you can do it by clicking on import dataset. And for CSV, you can click on from text read R. So this will allow you to import your this CSV file. So let me choose. So this is a CSV file, and I'll import it and just okay, it is just taking a bit longer. Yeah, so this is the CSV file, and I'll just import it here. Yeah. So we imported the CSV file, and we did it by using this import dataset option here. But another way to do the same thing is by using this read.csv function. And read.csv function is available in base R, so you don't again have to type the install.packages line. So you don't have to again install read Excel. You can just simply type this line of code if you want to do it by using code. So you can type read.csv, and within it you can do file.choose, and it will again open up a dialog box. and we can choose the CSV file here. And as you see, DF2 has been created. So yeah, these were two ways in which you can import your data sets into R by using import dataset or by using read Excel and read CSV. So we looked at some basic functions in R. We looked at how you can import your data sets in R and start working with it. So this is it for my part. In case you have any questions, you can ask them towards the end when we have the Q&A. Now Ritik will be covering the statistical tests in R. So yeah, this is it for my part. Thank you so much everyone for listening. And Ritik, over to you.
Yeah. Thank you so much, Pooja. So I think Arjun has something to say. Yeah, Arjun, please.
Sorry, I was just trying to clap my hands. I didn't find it right.
Okay.
Sure.
Thank you so much.
Sure.
In case
Let's.
anyone has any questions, I will take them towards the end. So yeah, we will have time.
Yeah. Just to confirm, is my screen visible?
Yeah, it is visible.
Okay, great. So, hey everyone, after that, those long two sessions from Arjun and Pooja, I'm not gonna take a lot of your time. Now I'm gonna just show you how to do basic tests in R. So at first, I would just like to do a check-in. So what is your understanding of R? What is your level of understanding in R? Are you a beginner? Are you, someone who has intermediate knowledge, or are you someone who has advanced knowledge? Can you let me know in the chat box? Okay. Yeah. Okay. So I can see that unanimously, most of you, I mean, are beginners in R, and I myself have started working in R only last year. So yeah, you'll realize that R is a super fun environment to work with, and it's quite intuitive as compared to other platforms, and you won't have you won't have any problem understanding a lot of things in R. So yeah, let's do this in R. So as Pooja talked about how to import your data set in R, now after we import our data set, what do we do with our data set, right? So that is what I'm going to be covering in brief today in our session. So whenever we load our data set in R, one thing that we should do, a good practice is to explore our data set. What do I mean by exploring is we should see, what are some of the descriptive stats of our data set? How does the data look? Does our data set contain any factors? What variables does it contain? All these kinds of questions, right? So today I'm going to be using Iris package and Iris dataset from the package Psych. So whenever we load some kind of package in R, we follow it with a library and then Psych. So today I'm going to be working with Psych package, and I'm going to be using the data frame dataset Iris for today, right? So that's what I've done here. So when I ascribe this data frame Iris to df2, which I've just used randomly as a variable name, I'm assigning this data set to this variable name, right? So I can just run this, right? So the way you'll run this is you'll just select it, and you'll press on run, and then it will show you a green temporary button on the left hand side, which shows that it was successful. And yeah, now when I want to simply talk about when I simply want to see what kind of what are the different descriptive statistics within this data set, that is Iris, I can simply use Psych package. So let me just load the Psych package first, and then I can just write describe, which is a function that I can use to understand the various descriptive statistics of my data set, which is df2, and I can just run it. And it will give you a nice table of different measures and different statistics of our data set. So as you can see, there are 5 variables in the data set. First is sepal length, then there is sepal width, petal length, and then petal width, and then species, right? Just to understand how does it look visually, I have a picture of a flower. So as you can see, the green part which is attached to the stem, it's the sepal, and the colorful part, the the visual part of a flower is the petal, right? So just to understand what our data set is, right? Now, as you can see, so you can see a small asterisk here, which says that these numbers do not mean much because this variable is a categorical variable, and you should just look at others, right? So for example, if I just go with one variable, which is sepal length, so it tells you how many number of observations do we have. So in this case we have 150 observations, and then the mean sepal length is 5.84, and the standard deviation is 0.83, and so on, right? So this simple command in R gives you a lot of information about your data set, about the distribution, about important metrics such as mean, median, minimum, maximum, right? Now, moving on, we can just check for our normality visually, right? So this step is quite important when we want to check our data set and we want to prepare our data set for various tests, right? So before we perform any kind of statistical test, we need to check the distribution of our data, right? So after performing the descriptive stats, we are now interested in how, if our data set is normally distributed or not. So when I say normally distributed, I mean the bell-shaped curve that we get, in most of the psychology books and in most of the, psychology basic stats classes that we have all covered and attended. So a data set should be normally distributed for parametric tests, and if it's not normally distributed, then we go for non-parametric tests, right? And if these jargons are quite new to you, so don't worry, we are going to cover them one by one today in brief, right? So one way in which we can check for normality in a very visual manner in R is making quantile plots. So what it does is, I'm just going to come to that in a second. So I'm just going to first show you what it does, right? So in R, I'm using the command qqnorm. And then when I mention, so first I have to mention the data set, which is df2 in my case. And then this $sign indicates the variable, right? So I'm just going to do it all over again for you. So first I'm going to mention the data set, which is df2. And then once I mention the dollar operator, it gives me all the variables that are contained in this data set, right? And I can just choose the one that I'm interested in. So right now I'm going to be checking the normality for sepal length, and and then the next command is qqline, which gives you a simple line that goes through your points. So I'm just going to show you visually how does it look, right? Okay. So as you can see, a quantile plot. I'm not going to go in much detail, but simply a quantile plot shows you the distribution, the sample distribution as per against the a theoretical quantile, which is the normal distribution, right? So just a thumb rule, if most of your points are lying on the straight line, as you can see here, then you can assume normality, right? But then in a lot of cases, it's not quite evident as per visual methods as per the graph. As you can see, a lot of these points are lying off the line, right? Are lying off the line. So in that case, we can go with our more robust statistical test to test for normality, which is Shapiro-Wilk test. In R, how we do with this is this command, which is shapiro.test, and then we simply run this function, right? So one thing we need to understand about Shapiro-Wilk is that if the p-value is lower than 0.05, which is our level of significance, and if you would recall, there can be different level of significances, as Arjun also covered in his part of the presentation. But in our case, the default level of significance is 0.05. And in our case, the p-value is lower than 0.05. Now in Shapiro-Wilk test, if the p-value is less than 0.05, which means the test output is significant. It says that the distribution, what it means is that the distribution is significantly different from a normal distribution, and hence the normality is not assumed in this case. So as you can see, the p-value is lower than 0.05, which means it is significantly different from a normal distribution, and hence we will not assume the normality of this particular variable, which means that this particular variable is not normally distributed. Hence, we can go for non-parametric tests, right? Yeah. Any questions till now? If you have any questions, please let us know in the comment chat, comment box, and we'll get back to you.
There is
Right.
one question in chat right now, which asks, is this uniform scale of measurement or do we convert it to some scale or numerical first?
Can you repeat the question, Pooja? Yeah.
So it says, are these uniform scale of measurements or do we have to convert into scale or numerical first?
Do you mean about the variables, or what exactly are you referring to? If you can make that clear.
Yeah, they are saying that yes, they are referring to the variables.
Right. So since we did not have much time, so that's why I didn't cover this very small but important part. So thank you for bringing my attention to that. So if you remember, I directly jumped to descriptive stats, but I wanted to cover the need, this command which helps us understand the nature of our variables as well. So there is a command called str command in R that helps you understand what are our variables even, right? What are we working with to begin with, right? So let me just type it out and then our data set. And if I run this, so this gives me that the data frame overall contains 150 observations of 5 variables, and sepal length is a numeric variable which has these numbers, and then sepal width, and then sepal length, sorry, petal length, and then petal width as well. And then it tells you that species is a factor which contains 3 levels. I'm guessing these are different colors, different species of the flower, which is setosa, versicolor, and then the third one, right? So when you use str command, you can understand the nature of your variables, if they are numeric or if they are character or if they are in factor, right? So in this case, by default, the species variable was a factor. Uh, it had a nature of factor, which means it's already categorized into 3 different factor. But at times, what happens is a lot of the characters variables are just written as characters. In that case, what you can do is you can just mention your data set first and then your variable, for example, which is species, and then you can simply convert it to factor. You can just use this command as factor, and then you can write the same variable, and then you can convert it to factor, right? In our case, it was already a factor, so it won't change here. As you can see, it will just show you factor with 3 levels. Yeah. Does that answer your question? Am I clear here? Any follow-ups?
They are asking, we don't have to change like we do normally in SPSS.
Yeah, because you need to understand one thing, that uh, a lot of things are already built in SPSS, right? So and SPSS uses a modular way of working. So for example, when I say a modular way of working, what I mean is that in SPSS there are already inbuilt functions. If you click on them, the system itself does a lot of your work. But in R, since it's a programming environment, you have to involve yourself in a conversation with R, and it is a step-by-step process, and it always helps you to explore your data set first. And yeah, I mean, you have to put in a lot of commands in R sometimes, simple commands though, to understand your data set much better. So yeah, I mean, I personally like R because of that reason, because it intuitively gradually builds your understanding with your data set of variables, of the distribution of their nature and everything else. Does that answer your question?
Yeah, they said thank you. It makes sense.
Yeah. So let's just continue. Where we left off was we were checking for a normality, and we can see that for some of the variables, the data set is not normally distributed, but for some of them it is. So for example, if I run for sepal width, the p-value is more than 0.05, which means that our distribution is not different or not significantly different from that of a normal distribution. or in short, the sepal width, this variable is normally distributed, right? And if we repeat the process for petal length, it says much lower than 0.05. Don't get confused by the e here. It simply means 7.412 into 10 to the power into 10 to the power, yeah, minus 10, right? So it's like 0.00000, right? So it's much lower than 0.05. It says again not normally distributed. And if you go for petal width, not normally distributed as well, right? So as you can see, only sepal width is normally distributed. Rest of them are not normally distributed. Now, the most basic statistical inferential test that we are going to be covering today is correlation between variables. So just to reiterate on what Arjun also mentioned in his part of the presentation, correlation test is used when we want to test the association between two variables, right? When we want to understand if there is an increase in one, is there a parallel increase in the other, or is there a decrease, right? And as you would recall from your statistics classes, or just generally, if you have read about correlation tests, the value ranges from -1 to 1, where -1 indicates a perfect negative correlation between two variables, which means that as a increases or as x increases, y decreases, and a positive correlation would mean as x increases, y also increases. And when the correlation is very close to zero, it means that there is no relation or very weak relation between these two variables, right? So now we are interested in understanding the relationship between sepal width and sepal length, right? So just to visually see this, so sepal is this. As you can see, the width is pretty small and the length is pretty large. And so we're just going to be understanding, is there any link between these two? Is there any correlation? Is there any association between these two? So before going ahead with any statistical test, it is always great to visualize your data, right? It's always great to visualize your variables. So that's what we are going to do today. So before trying to understand the statistical relation between these two variables, let us just try to plot. So our x becomes the sepal width, and our y becomes the sepal length, right? And to do this, we simply use plot function, which is inbuilt in R, right? For which you don't have to load any package. If we run this, it gives us this graph, a pretty graph that contains random dots, right? But we can't infer a lot from this, right? So what do we do is we just add a line, a regression line. So if you would recall from Arjun's presentation, a regression test is simply used to understand if x predicts y, or if y is predicted by x, right? In other words, so simply we use this command called abline, and then we mention the regression, which is using linear model LM, short for LM, and then we say y, we prescribe y, and then we prescribe x, right? So if I were to put this in simple words, I would just say y regressed against x, which says that y is dependent on x, right? So when I use this small symbol, I think it's called tilde, right? It says that y is dependent on x, right? Or in other words, x is the independent variable or y is a dependent variable, right? So in this case, none of these are independent or dependent. I just want to check the association between these two, and I just want to see the line, right? So I'm just going to run these two together. And as you can see, it gives me this slightly slant line, which goes down as we move around in our x-axis, which says that as the sepal width increases, there is a slight decrease in the sepal length, right? And now to just check this statistically, we are going to run our Pearson's correlation test. While I prescribe Pearson, what I mean is it's a parametric test, because one of the variable was normally distributed, right? And we can go ahead with set it with a parametric test here in this case. So how you can do this in R is quite simple. Either you can write simply COR command, which is an inbuilt function in R, and then you mention your x variable. One second, you mention your x variable, which is sepal length, and then you mention your y variable, which is sepal width, right? And by default, the method that that this function will be using is Pearson. But if you want to go for spearmint or candle that we are going to be just covering in a minute, you can mention using this argument, which is method, right? So in this case, I'm just going to be going with the default method, which is Pearson. So let me just run this. So it gives you simply a measure of the correlation between these two, which is slightly negative, minus 0.0 minus 0.11. And since it's quite closer to zero, we can say that it's a weak correlation, weak negative correlation, right? But we want more information about the test, whether it's significant or not, what was the difference, and all other information. For this, you can use core.test, right? And it gives you much more information. More importantly, it gives you this measure of significance, which is the p-value, and it tells you that it's more than 0.05, which says that of course there is a slight negative correlation, but it is not significant, right? So what you can say is, even though there is a slight negative correlation between these two variables, it's not significant, and hence there is no significance association or correlation between these two variables, which is sepal length and sepal width, right? And suppose we want to do a non-parametric test that are spearmint and Kendall's test in R in generally as well. So spearmint and Kendall's correlation, we can simply mention the method as spearmint. And now we want to understand the relation between petal length and petal width, since they both were not normally distributed. So that's why we are mentioning this method as spearmint. Now if you run this, it gives you simply that, oh, there's a very strong correlation, but we want more information, of course. So we can just use core.test, and then let me just remove this error. Okay. Okay. Yeah. So it gives you this measure of Spearman's row. So in Spearman's case, it's not R that you get. The matrix is the matrix that you get is row, Spearman's row, and it's, as you can see, it's quite closer to one, which is a perfect correlation between two variables, perfect positive correlation, right? And the p-value is much lower than 0.05, which was our level of significance, just to reiterate. So you can confidently say that petal length and petal width are significantly correlated to each other in a positive manner, or there is a strong, very strong positive correlation between these two variables, right? Now, are there any questions till
Nothing
now?
in the chat so far.
Yeah, is everyone able to follow up? I think I would like to ask that first. Can you let me know in the chat box if you are able to follow up till now? And if you have any questions, also don't worry, we are going to be sending you this Arch markdown file as well, so that you can do this on your own as well. Yeah, and also the recording will be shared with you all as well. So is it clear till now, everyone? Can you just give me a thumbs up? Okay. Yeah, Tanisha, I'm just going to be coming to that. Okay. For others, is it clear? Yeah, definitely, Mahalakshmi. So don't worry about it. I understand that R can seem daunting at first. It was daunting to me as well. But yeah, I mean, once you get your hands dirty with it, it always is a fun journey. And yeah, the point is we should grow a little bit step by step, and yeah, that's the point. So yeah, I'm just going to be coming to the question that Tanisha asked. So back to my R studio. Yeah. So yeah, I didn't want to jump to this because it's a bit advanced, but we need to understand that the non-parametric tests that are Spearman and Kendall, they are usually used when we have variables that are ordinal in nature, right? And as you would recall, if you have learned about this, or generally, if even if you don't know, that's all right. So ordinal variables are the ones that have ranks, right? So for example, yeah, when I say someone has, you know, grade A, so or a student has grade B, a student has grade C in Indian education system. What I'm saying is that a student who has a grade A is better than a student who has a grade B, or or the student has performed better. Just to rephrase myself. So a student who has a grade A has performed better in a test as compared to the student B, who has a grade B, of course, the student 2, and so on, right? So in this case, there is a certain rank to the different values in my variable, right? So this is an ordinal variable. For example, it will go to, let's say, grade F, right? So which means that grade A is the best and F is a failing grade, right? Which means A is better than B, which is better than C, which is better than D, and so on, right? So it's an ordinal variable. In this case, what happens is, how Spearman's correlation is calculated is, it is calculated through different ranks, right? So what it does is it calculates ranks with the other variables. So there is your one variable X, and then there is your second variable Y, and then it calculates different ranks with these, and then these ranks are tied upon, and that's how it is calculated. I know it may sound very complicated right now, and I really don't want to jump to that right now. So just understand this one thing, that exact are the ones that are used for exact ties. But if I don't want exact ties, I can simply write I don't want exact ties here, and this warning will be removed. So since it's a bit advanced, I'm not going to be going in much detail, Tanisha, but don't worry about it. If even if you get that warning, don't worry about that right now. So as you can see, the row does not change at all. It's just that this warning tells you that it cannot compute exact p-value with ties. So we mention it explicitly that please compute exact p-value, like don't compute exact p-values, right? So yeah, don't worry about that right now. There is something that will come much later. And gradually, as you start doing your correlations, your basic tests, now you're going to be learning more about how these functions are actually working, right? Yeah. Now, so yeah, I'm going to be taking a brief example, another example which is more relatable, right? So I realize that that iris dataset may not be quite relatable. So I'm going to be using this dataset called salaries dataset, which is contained in the package R. So I'm going to be loading the package first, right? And then I'm going to be loading my data set, which I now call df3. So if I want to see df3, you can see this simple and pretty data set. So it gives you the different ranks of 397 professors, as you can see here. And then it also tells you discipline. Here B means that they were applied, that they work in an applied discipline, and A means that they work in a theoretical discipline. And then these are the number of years since their PhD. So this professor has covered 19 years, 20 years, 4 years, and so on. And then number of years of service they have given to their tenure. So for some of them it was 18, 16, 33, and so on, right? And then there's sex, and then salary, right? These are the 6 different variables that are contained in this data set. And now we are just going to be briefly talking about this, right? So let us just first see what is the nature of our variables in this data set. Yeah. So since there are network issues on my end, I'm just going to be switching off my camera. Yeah. So as you can see in this, when I run this command called strdf3, I get more information about my variables. So it tells you that there are different variables. So let's go one by one, right? So the rank variable is a factor that has 3 levels. There is assistant professor, associate professor, and professor. And then the discipline is also a factor which has 2 levels, A and B. And years since service is an integer or number, and years in service also an integer. And then sex is a factor with 2 levels, female and male. And then salary is an integer with which is a continuous variable, right? So as you can see that there are 3 variables which are continuous in nature. That is years since PhD, years of service, and then salary, right? And then simply, if I want to see the normality of salary, the variable, I can run my QQ norm and QQ line plots. Yeah. So of course, visually it says that it may be normal or it may not be normal. Definitely something that we can only test through Shapiro test. So it's quite so the p-value is much lower than 0.05, and it tells you that that the salary this variable may not be normally distributed, right? Now, we need to understand one thing is that the assumption of normality also has received a lot of debate, right, over the years by different statisticians, psychologists, and people who are working in the field, right? So, when it comes to a lot of observations, such as in this case, where the data set contains 397 observations, the assumption of normality can be loosened up, right? It is not as strict as we would like to believe, right? So, but then in cases of small sample size, such as when your sample size is 40 or 30, or 35 or even like 70 or 80, in that case, it makes more sense to have a stricter criteria for normality. But when you have a lot of participants in your data set or in your study, then the normality assumption can be relaxed in a few cases. So I'm going to be coming to that as well briefly. So now, for example, if I want to understand the relationship between years since PhD and the salary of a faculty, right? So I want to understand if the salary of a faculty of a professor has increased um, since their PhD or not. So first, I can just simply plot with x variable as years since PhD, and then salary as my y variable on the y-axis. And when I plot it, it gives me a pretty plot of random dots, but again, it does not tell me much. So I can just put in another command, which is abline, which gives me a regression line, right? Just give me 1 second. I need to run this together, right? So it shows that there is a positive relation between these two variables, or simply as the number of years since PhD have increased, the salary of a professor has also increased slightly, right? And now to confirm this, I can just like do a correlation test, and the method that I'm going to be using today is Spearman. But again, if you have a lot of observations in your data set, you can go ahead with Pearson as well. Yeah. So as you can see, there is a medium, uh, moderate strength of correlation between these two variables, which is 0.47, which is still a good correlation. If we think about all those, if we think about psychology as a science, right, we don't get something like this quite a lot, right? So yeah, you can say that there is a moderate, positive relationship between years since PhD and the salary of a professor. Or in other words, as the years since PhD increase for a professor, the salary also increases for them, right? Now moving on, let me just, yeah. Now, for example, if we have a research question that says that do professors get different salaries as per their ranks? So, if you can recall from your institutions, you can definitely tell that someone who is an assistant professor is lower in rank as compared to an associate professor, and a full professor is definitely above, associate professor and assistant professor in terms of rank, in terms of their, rank in an institution, and it's mostly, as per one's experience, right? So, the hypothesis that I'm going to be going ahead with is a null hypothesis, which says that there is no difference between the professor salaries as per their rank. And now, just to show you, there are three levels within rank, which says if someone is a professor, or someone is an assistant professor, or someone is an associate professor, right? Now, just to reiterate, the null hypothesis would be there is no difference between the professor salaries as per their rank. So now, as you can recall, now if you want to understand the difference between means of different groups, right, we go ahead with either t-test or we go ahead with ANOVA, right? Can someone tell me in this case where we have three ranks of professors here, what test would be appropriate? Will it be a t-test or an ANOVA? Can you quickly tell me in the chat box as per your understanding? Yeah. So, Sanjana, you're right. So we're going to be using ANOVA and not t-test here. It's because the groups that we are comparing here are more than two, which are like three groups here. That is, we want to compare the salary of a professor versus the mean salary of an assistant professor versus the mean salary of an associate professor, right? So for that reason, we are going with the ANOVA test, right? So we can simply call a variable test for professor salary, and then in R you can simply use the function AOV, and then you can put your y variable on the left hand side, which says that I want to regress salary against rank. I can just simply remove this factor. This is not required here, which says that I want to see if rank affects salary or not, right? Where your y variables goes on your left hand side, followed by a tilde, and then your x variable, and then I mention my data set, right? So when I do this, it stores my formula and what I want to do within a variable called test for professor salary. And now when I want to see the summary of my statistical test where I get different metrics, right? I can simply run this summary, right? So it tells you that rank as a factor does play an important role in salary for a professor. As you can see, the p value is much lower than 0.05, and it also tells you this nicely put scheme of significant codes here, which says that if it's zero, which means it's much significant. If it's less than 0.001, there will be 2 stars. If it's lower than 0.01, then there'll be 1 star, and then so on, right? In this case. So it tells you that rank as a factor does play an important role, does play a significant role in salary, right? So you can confidently say that you can confidently reject your null hypothesis and say, we reject a null hypothesis which said that there is no difference between the professor salaries as per their rank, right? And then we accept an alternative hypothesis here. And as you can see, I have done this for two more questions here, and you can explore this on your own. And because of the time, we don't have the bandwidth to cover these two questions here, but definitely these are quite interesting about this data set as well. I can simply just tell you more about it. So one is about, do professors get different salaries as per their orientation, that is theoretical or applied, or not? And then another is about, do professors get different salaries as per their sex or not, right? Which simply means that do like among the two, which is males and females, who gets higher salary, right? And to do this, you simply use t-test. So in R, you write the command as t dot test, and then you put your y variable in the left hand side, and then your x variable on the right hand side, which says that I want to compare salary against discipline. And there are two disciplines here, A or B, and since the groups will be two, then t-test is appropriate. And in this case too, where the groups are just two, males and females, they have not taken data from other sexualities, right? So in this case, the the groups will be two as well, and for that t-test would be appropriate, right? So this was a quick summary of like brief summary of different tests that you can do in R. And if you have not understood anything from these, any part of these, don't worry. We are all beginners with R, and it's going to be a step-by-step journey. And this video is going to be shared with you along with the R Markdown file, and you can simply replicate it in your own files in R, and do reach out to us in case you have any questions. Yeah. So that was all from my part. Arjun and Pooja, if you have any inputs for this, please jump in, and yeah.
Thank you so much, Ritik. That was really wonderful presentation. I really like the example you used towards the end, comparing the salaries. And yeah, it was great. And thank you, Arjun, for your presentation. I really had fun listening to both of your presentations, and it was amazing.
Yeah, and thank you to both of you as well. R does not seem that scary anymore. I had tried to use it once, but I got scared just looking at it. But hopefully not anymore.
Yeah, so just before we close the session, we can take in a couple of questions. Is that all right by Pooja and Arjun?
Yeah,
Yeah.
of course.
Do we have any questions? Please, guys, let us know. Or
Also,
even if you
if
have, yeah, please go ahead.
if you want to stay connected, we have a Slack space for the club where you can keep asking your questions or doubts as you learn R. So we also have a Slack space. You can join the Slack space if you just send us an email here. So if you just send us an email, we will add you to the Slack. So as you learn R, you would have many questions and doubts. So you can just join the Slack space and keep asking.
So I'm guessing there aren't any questions. And if you, even if you have any questions, please reach out to us on this email ID. And you already know Arjun's, um, you know, LinkedIn ID and stuff. So Arjun, you can also type in the chat box where can people reach out to you on your public profile. Yeah, I think that will be great.
Sorry, I dropped
Thank you
out there.
so much, everyone. Yeah,
Thank you
no
so much.
worries, Arjun. Okay, I don't think there are any other questions. Thank you, everyone, for joining, and it was amazing to have you all here. In case later there are questions, feel free to email us. So, yeah. Thank you, everyone, and thank you, Arjun, for joining us. Thank you, Ritik.
Thank you.
And wait, what is this? This was the name. Okay, thank you, Isha. We will surely definitely have more sessions. Thank you so much.
Thank you, Pooja. Thank you, Ritik. I'll drop out now. See you
Sure.
again soon.
Okay, thank you, everyone. I'll end the meeting now. Thank you.
Yeah. Bye bye.